So the last piece of the puzzle in this overview section is to talk about the subclasses of Java ForkJoinTask. And these will end up being RecursiveTask, RecursiveAction, and CountedCompleter. RecursiveTask is particularly important because this is what you'll be using in your programming assignment. So let's talk about these. Programmers rarely implement ForkJoinTasks directly, although it's not uncommon to have a list of ForkJoinTasks or an array of ForkJoinTasks, but you typically don't implement the ForkJoinTask because there's better ways to do it, as we're going to see. Instead, what they do is they extend a subclass of ForkJoinTask, like RecursiveTask or RecursiveAction and so on, and then override the compute hook method that it defines. So you'll see that's usually the way that you do this. It makes the programming model very simple or simpler from your perspective. It's not as simple as using functional programming, but we'll get to that later. So let's talk first about RecursiveAction. This is useful for computations that do not return results. They just want to split things up into chunks and then process them in parallel, but they don't specifically return a result. And you can see that there's a void return value from the compute method. This is ideal for scenarios that perform actions like data modifications, I/O operations, or any other type of side effect-oriented processing or computations or operations that don't need to return a result. And I'll show you some examples of that when we look at some case studies later. The next model, which is probably more common in many cases, certainly you'll get a chance to play with it, is RecursiveTask. And this is used for computations that do return results. So you can see here that unlike RecursiveAction, which did not take any parameters, the RecursiveTask takes a parameter which is v, which is the return value from compute. So compute's going to return a value of type v. This is ideal for scenarios that need to process data in parallel and then gather the results together and return the results. For example, if you're going to be doing some kind of image crawl, you might want to return a count of the number of images that you crawled at some level in the recursively structured directory or folder hierarchy. So that would be the way you would do it, through a recursive task. And then there's also another model here that's called CountedCompleter. And this is one that you typically don't subclass, but there are other people who write Java internals that do. And this is useful for computations in which the completion of one action triggers a bunch more things. And so this is very useful for scenarios where tasks may generate an unpredictable number of subtasks, and then some action must be performed once the task and all its subtasks complete. So this is actually what's used internally in things like the Java Completable Futures framework. I think it's also perhaps used in Java Streams, but it's definitely used in Java Completable Futures. More of an internal thing, just showing you there for completeness if you ever run across a CountedCompleter. Now, the thing to keep track of here, because it's kind of annoying at some level, is that this whole framework was developed in the Java 7 timeframe, which was 2010. That's before the architects and developers of Java had this wonderful epiphany and realized that functional programming could simplify a lot of aspects of doing software development in general, and in particular for parallel and asynchronous programming. And so as a result, what you get here are subclasses that aren't based on functional interfaces, even though they only have one method called compute. The whole framework is not a functional framework. And therefore, if you want to use these classes, in particular RecursiveTask and RecursiveAction, or ForkJoinTask for that matter, you need to subclass them using white box reuse techniques and then override the compute method, or the ForkJoin method up here, and rather than implementing compute. So just always keep that in mind, that under the hood, there's some things that are going on here that make it a little bit harder to program. However, the good news is that these other Java parallel frameworks, like Java Parallel Streams, and then arguably Java Completable Futures, although let's keep that off to the side for now, Java Parallel Streams provides a nice functional facade that hides all the underlying gobbledygook that are going on with the ForkJoin framework. So internal to the Streams implementation, which we will look at later, especially the Parallel Streams implementation, there's the use of the ForkJoin framework, but it hides all these details behind little facades. And so you just program a pipeline of so-called intermediate and terminal operations, and those operations are passed so-called behaviors. Those behaviors are functional in nature. They're method references. They are Lambda expressions. They're implementations or instantiations, if you will, of functional interfaces. And therefore, all the details of the fork join framework goes away. And you'll get a lot of chance to play around with that in an upcoming assignment, which will take what you did in assignment 1 and then simplify in several steps the various stages by using streams and parallel streams. So that's the end of our discussion on subclasses in the fork join task.